Hello everyone, today our group will talk about SQUID, but not the SQUID you are thinking right now. It's called Superconducting Quantum Interference Device. SQUID is an ultra-sensitive detector of magnetic flux made up of a conducting ring interpreted by one or two Josephson junctions. As you can see from this diagram, there are two Josephson junctions. So next, there are two theories about SQUIDs, and one of them is magnetic flux quantization. This phenomenon was discovered experimentally by B.S. Lever and W.N. Fairbank, and find out by R. Dot and M. Nebel in 1961. Fundamental of an electron charge is equal to 1.6022 times negative 19 coulombs. Magnetic flux is quantized in step of phi not equal to h divided by 2e, which is equal to 2.0678 femto Webers, where the h is the Planck constant.
So for the next one is the Josephson tunneling effect, which is it's a phenomenon in which the current flows without any voltage applied across a junction, which consists of two superconductors coupled by weak links. So the weak link may be composed of a thin insulating barrier known as a superconductor-insulator-superconductor junction, which is we call it as SIS. Other than that, a short section of non-superconducting metal, or we call it as SNS. Or the other one, we can use the weak link as physical constriction that weakens the superconductivity at the point of contact. So this figure shows a Josephson junction, which is made of two superconductors connected through a small insulating layer.
There are two types of SQUIDs, which are the direct current SQUID and the radio frequency SQUID. A SQUID consisting of two resistively sheltered Josephson tunnel junctions is a DC SQUID. A bias current I enters and splits into the two parallel paths, each with current IA and IB, while the phi represents the magnetic flux threading the DC SQUID loop. In the condition of no external magnetic field applied to the superconducting loop, the input current will split equally. However, if a small external magnetic field is present, a screening current starts to circulate in the loop that generates a magnetic field cancelling the applied external flux. A voltage appears across the Josephson junctions when current is either one of the parts exceeds the critical current of the junction. Now let's move to the graph. The graph shows that the current voltage characteristic at integer and half-integer value of the applied flux, and the operation point is set by the bias current. The next graph shows that the voltage across the SQUID oscillate with increase of the period phi with a constant current above threshold.
Right, so for the RF SQUID, so as opposed to the DC SQUID that has explained by Lim Soo Sim, which has two junctions, but the RF SQUID is composed of just one junction. So the RF SQUID involves a single Josephson junction interrupting current flow around a superconducting loop and is operated with a radio frequency flux bias. So in order to fully account for the behavior of the RF SQUID, we must look at the inductance of a Josephson junction in an external field. So this figure shows a one-junction superconducting loop in an external magnetic field. So we can see that from the above is a basic circuit of RF SQUID, which is a one-junction superconducting loop coupled to a LC circuit with an alternating current source of radio frequency. Alright, so the RF frequency SQUID is a one-junction SQUID loop that can be used as a magnetic field detector. So although that it is less sensitive than the DC SQUID, it is cheaper and easier to manufacture and is therefore more commonly used. So the quantum design SQUID make no spectrometer that is frequently used by experimenters. For example, use a one-loop RF squid. So comparatively, RF squids are less sensitive than DC counterparts as they employ only one transception junction, and for this reason they are less expensive, as I said before. So the applications of squids are wide-ranging. So from the detection of tiny magnetic fields produced by the human brain and the measurement of fluctuation geomagnetic fields in remote areas to the detection of gravity waves and the observation of spin noise in an ensemble of magnetic nuclei. So that's all from us. Thank you.